high-level introduction to artificial intelligence and machine learning. And as we get more and more into the meat of what it is, Monty will take over and it's going to get very complex. But I think because Jason couldn't come, we'll have time for questions and answers, and we'll take our time going through the slides, if that works for everybody. Trying to get to the next slide. It's a little bit of a delay, I think. Oh, there we go. So I think we already covered this. We're Santa Fe. We're located in Santa Fe. We're woman-owned. I'm the 51% owner, a tech startup. And as Manchi mentioned, we believe that we can use our artificial intelligence tools to help with some of these environmental problems we're facing. So artificial intelligence, really high level, is intelligence achieved by machines. This is opposed to natural intelligence, which is displayed by animals, including humans, human animals. Machine learning is a subset of artificial intelligence, and it's a building block, or another way to say it is it's a building block of artificial intelligence. It's a scientific field devoted to building methods that learn from data. Machine learning uses data and information to develop machine learning models. Machine learning methods make predictions and decisions. And machine learning achieves this based on provided data and knowledge known as training data. Machine learning is essentially a black box with a network of neurons that must be trained. These are called black boxes because we don't understand how they work. However, we understand the training data. We also do not know if they can work in all cases. So there's some important terms that we use when we talk about machine learning. These are just the very high-level basic terms. We use algorithms quite a bit, which are a set of instructions to solve a particular problem. You've probably heard of computer algorithms, but algorithms can also not be used for computers. It's a very general term. Neurons are a series of algorithms or algebraic expressions that work to recognize underlying relationships in a set of data through a process that mimics the way human neurons operate. A neural network is a system of neurons, either organic or artificial in nature. And a machine learning artificial intelligence platform is a software code that tells a computer how to simulate a cognitive function of a human brain, such as problem solving, learning, reasoning, social intelligence, as well as general intelligence. So imagine you're building a model to reproduce outputs, and that's in that section Y, and with a given function, and you have the data X. So what you have is X and Y, and you're trying to figure out what F is, that function. So at first, the neuron knobs don't know, they haven't been trained and the data doesn't understand. So the initial outputs of the function don't really give you Y. But slowly over time and through extensive training, the knobs are adjusted and you can reproduce those outputs and find that function F. And I like this picture because it's funny because the dog is sort of like training itself, which is what the computer does. So finding neuron knobs and settings for any given X, the black box model can actually reproduce the Y. So machine learning data is an essential component. In fact, you can't put like garbage in, it won't work. You have to have really good, clean data. And sometimes that data is even created by algorithms because you're using it to train. Optimization is also a critical step of machine learning. Optimization is adjusting the neural knobs until they accurately predict the correct output. All the knobs on the neurons are optimized simultaneously to reproduce the training output. So I'll let Monty take over from here and mute myself. Are you good to go, Monty?
Yeah, and if I can switch to sharing myself, if you don't mind, just a second. I'm still confused how to share here. Share screen. Sorry, now I see how I can share. Just the computer is so slow. I'm not sure why.
That's okay. I'll check in with people while we wait for that. Anybody, how's it going so far? Is it kind of making sense? Yeah, I see a few nods. Great. Monty, I can hide myself to save some bandwidth if you want.
No, I apologize. I think Zoom is very slow. We'll see how it goes. Do you see my screen now?
Yes.
However,
You want to put it on slideshow? I'll come show you.
I know, but I still cannot see it. My problem. I know how.
Yeah, it doesn't show. I mean, it'll show on your extra screen, but you're
I
good.
know. I mean, I still don't see anything, unfortunately. I mean, my computer is not responding.
It says loading now. There you go. Perfect.
I still don't respond on my side. My computer is slow.
Do you want to come drive on this computer? Sorry, everybody. You want to come here?
Just a second. I don't think I'll be able to come over here because let me restart again. There's something wrong here.
Well, while he's doing that, I can just talk to you about the next slide if you want, which you can't see, but I'll just start talking so we're not getting bored. So there's different kinds of models you can use and different methods you can use to develop these models. There's statistical methods, there's machine learning methods, and then there's science-informed machine learning methods, which is what we usually focus on in our business. And science-informed machine learning means that we use science in part of the metrics of developing those functions. So, for example, conservation of mass can be applied into that learning into the algorithms, and it helps train better and faster because we have this. You're good, Monty. We have this these constraints from science involved.
So I mean,
keep going.
Okay. So you see my screen. I'm something is very strange. I don't see what I'm sharing, but hopefully everything works. So hopefully you see my slide, which states the data is essential component. So when we analyze, when you perform machine learning, we need to have data, we need to have knowledge, which gives us information of what we're doing. Optimization is done when we perform the analysis. And this is also another critical step. This is adjusting the knobs of the neural network. And all the knobs need to be trained in simultaneously. And I'll show in a little bit how all this works. I think Trace emphasized frequently when we talk about different models, we talk about statistical methods, we talk about machine learning methods, and mostly now we talk about science-informed machine learning methods, which allow us to bring science in the machine learning process. This is knowledge that we have about what we're trying to solve. There are various languages, computer languages that are applied to perform machine learning. Python, most probably almost everyone heard about it. It's a very popular language, widely used for machine learning analysis. However, there are new type of languages that designed to address a lot of limitations that Python has. And Julia is one of those languages. Sorry for the typo. I see it's supposed to say novel language designed for from very beginning to perform machine learning utilizing high performance computing. And when I say high performance computing, means things that we can execute on the cloud or on special machines that allow us to perform this type of analysis. So there are many challenges when you perform machine learning. Typically, you're dealing with large, high-dimensional data sets. And when we say high-dimensional, means that we're dealing with multiple coordinates. This could be X, Y, Z, time, and many other attributes that we can analyze. Obtaining the data by itself is a challenge because most of the data either is not easily accessible or requires special capabilities to get the data that you need to perform the machine learning analysis. When we are performing machine learning, a key aspect is optimization, as mentioned earlier, and typically this optimization is also challenging. And to address this, we frequently use penalties or regularization terms, something that constrains the problem and tells it more about what you're solving and can help solve it more efficiently. So machine learning allows us to make predictions. Typically, using machine learning, we perform two types of analysis, regression and classification. And I'll talk a little bit later what is the difference between those terms. Can be applied to quantify uncertainties in what we're doing, how uncertain we are in our predictions. We can also compute some kind of sensitivities, which means how sensitive the machine learning model is to what we're getting out. In some cases, this machine learning model could be very robust and accurate, regardless what the inputs are. In many cases, might be very fragile. And we need to know how fragile or how robust our machine learning model is. And based once you build the machine learning, you can do a lot of things which allow you after that to perform decision analysis, to apply it in your decision framework, whatever you want to use these machine learning methods for. So it's very, very important to understand the whole process and where you're going when you perform machine learning analysis. Platforms are frequently designed to support this process. I mean, there are a lot of attempts to make life of the developers of end users as easy as possible. You don't want, in many cases, to really start with computer language code. They are plug-in approaches where you can just upload the data and allow the machine learning to be executed in the background. And Google, Facebook, Microsoft, all these companies currently have such a platforms that you can plug in your data, perform the analysis, and achieve your results. In our company, we are using smart tensors. As we usually describe our machine learning process, we have nuts and bolts, which are the building block of the machine learning. And all these nuts and bolts for us live in the Smart Tensor platform, which is open source and everybody can use it. Everybody can execute analysis there. We have interfaces that allow us to do this, which I will show in a little bit. And we also have materials. I mean, I provided a bunch of links on the website, which are discussing workshop materials and tutorials that people can go through. Many of those are relatively high level, not as easy to use as would like them to be. So our tutorials and workshops are strongly recommended, but you need to really be passionate and devoted to go through exercises because it's relatively demanding to perform this. I'll be talking one example, will show you one example in a little bit, how it works and how it can be executed. This graph shows a lot of approaches which can be used for machine learning. Typically, machine learning is grouped in three methods: unsupervised, supervised, and reinforcement learning. And around them, they're showing different type of applications. I mentioned earlier classification and regression. Another thing that potentially you heard before is clustering. This is when you are grouping the data based on some property to understand being the data in multiple clusters. Dimensionality reduction. This is when you're dealing with high data with high dimensions and to compress the data and make it more manageable. One thing which is very important is that in all these cases, in addition to the data, we can also add knowledge, physical knowledge, knowledge which can help the machine learning process. And adding additional knowledge to the data is very important. I will talk a little bit, I mean, just to distinguish what is supervised and unsupervised. Supervised machine learning is the one that most of you frequently heard, the most common approach that have multiple uses that maybe you have seen is when you apply machine learning to recognize cat and dogs. So you have algorithm, you provide images of cats and dogs, and the algorithm automatically tells you this is a cat, this is a dog. However, to do this, you need to have huge amount of data. Facebook and Google at the moment use the images that people upload on the network, and when they label them, oh, this is a beautiful cat, or this is the dog that I went to a walk in the afternoon, they use this information to train their algorithms. However, we are the one that we are providing this information. All of us that post images of our pets provide information for Google and Facebook to train the algorithms to recognize cat and dogs. And this labeling process is the most important for supervised machine learning. You need to have labels. Requires large training data set. Typically, we use millions of images to learn to recognize cats and dogs. However, we don't understand really how the algorithm distinguishes between cats and dogs. We know that it works. However, exactly how it works is very challenging. The analysis that show how the algorithm can identify features in the image that it's analyzed, and based on the shape of the ears or shape of the eyes or shape of the face, they can recognize it. However, one of the important things is that very frequently these algorithms can be fooled. And what I'm showing on the bottom is that you have image of panda that the algorithm recognizes very well. However, if you add a noise to the image that you cannot see, which is on the right, so the right is the same image but added with a noise that you cannot see, actually the algorithm can be totally fooled and think this is a different animal. And there are many examples like this, maybe you have heard, but there are many cases that you can fold algorithms, and this relates to what I was talking earlier about the robustness and trustworthiness of machine learning, that you need to be sure that it's working properly. You don't want to have these situations. Unsupervised machine learning methods or self-supervised machine learning methods, they extract all the information from the data. You don't need to label anything in advance. You put the data and the algorithm analyzes the data. And here is an example in the figure below how the algorithm can learn what the important facial features. In this case, this is from work that originally was done like 10 years ago, and it was published in Nature. You have 1,000 images of different people, and you analyze these images and you find common features that exist in these faces. You find common eye shapes, common nose shapes, common eyebrow shapes, chin. And this is on the left is the dictionary of the faces. So the algorithm identified 49, 7 by 7, 49 different features in the face, which are common for all people that were analyzed. And after that, reconstruct the image or the face that you see on the right by combining facial features on the left. And this, in the center, this matrix shows which of these facial features are present in this face. And the one which are with black, which is 1, and zeros are white. So zeros are features that don't exist, and black is features that exist. So now when you look in the first row, there are 2 gray and 1 black box, and the other ones are white, which means that the first image, which is not very recognizable, or the first feature, this feature and the last 2 features are not present. However, this feature, which is black labeled here, is important to reconstruct the face. And again, you can go through each of these rows and see which features are important. All the black features are the ones that are critical to reconstruct the face, and the other ones are not. So now you can imagine how this can be important for any type of problem where you have data, you don't understand what does it mean, and this helps you to extract features out of this. After that, also you can find all the people that have specific eyebrows or all the people that have specific nose shape. So you can group the people based on what they have in their faces. I hope this makes sense. I mean, please feel free to interrupt and ask questions. I'm also kind of monitoring the chat. So if people put questions in the chat, I'll be able also to answer. But this is one critical distinguishing point between self-supervised or unsupervised machine learning methods, which I'm describing here, and what I'm showing on the previous slide, supervised. And the third group of methods that we'll be talking a little bit, but just to add explanation, and we mentioned this earlier, is science or physics for machine learning methods, where we're adding knowledge based on the problem that we're solving. We're adding subject matter expertise in the machine learning process. So I don't want, I mean, I'll show you demonstration in a little bit, but before going there, I'll just also show how this paradigm of science-informed machine learning relates to what we have been doing for years in the science domain. You have data, you have a lot of math, statistic, and computer machinery that exist, and you have scientific knowledge. And when you do machine learning, you're intersecting the data and the math and techniques. When you do empirical research, which was done for centuries, starting from Galileo,
you are merging data and sciences. And when you do theoretical research, you are using math equations to predict the science. So you can think about three major ways that we're trying to understand how the world is manifesting itself, to understand the laws of nature, to understand the meaning of life. When we combine all of this in the center is what potentially can call science-informed machine learning. And recently also another popular term that it's coming in mind is multimodal foundation models, but I don't want to go there. But when you think about multimodal foundation models, you can think about ChatGPT or Google Bard that can solve machine learning problems directly for you and perform artificial intelligence to solve science problems. So I can think as multimodal foundation models as a scientist who are doing all the work for you. You just ask the question how the galaxies are formed, and the algorithm performs the simulations and analysis of existing data and give you answers how the galaxies are formed, for example. But this is really very much on the high level. There are different ways to add the physics information in the machine learning process, but let me show something more potentially easy to understand. I mean, just to demonstrate how everything works. Do you see my screen now, which is showing something that says natural work networks?
Yes.
Okay. And apologize, I don't see anything. I'm not sure why I cannot see, but hopefully you can see it. So this is a playground for TensorFlow. TensorFlow is one of the packages developed by Google. It's widely used for machine learning. The other package that is widely used is PyTorch, developed by Facebook. And this is a TensorFlow playground. And I'll just demonstrate how it can be applied. As mentioned earlier, frequently we are talking about classification and regression problems. I'll start with classification problem. So in this case, you have orange and blue dots. You have some domain on the right, which represents, you can think about this as, let's call it, I mean, let's say, for example, if this is characterizing habitat of animals, and the orange dots show the locations in which cats live, and the blue dots are showing locations where dog lives. So the task of the algorithm is to identify the border, the boundary between those two domains, between the blue dots and orange dots. And for us, could be trivial because with our eyes, we experienced, we can look at this and say, oh, I can draw the boundaries, this very simple circle between those two. However, the algorithm or the computer does not have our cognitive capabilities until it's trained. So when you press the play button here, it will start training. And there are a bunch of things that here control the behavior. This is not important, but I'll press the button and try the algorithm now to train it. And what you're seeing now, the algorithm is trying to identify two regions, orange and blue. And I'll start it again. As you can see, initially it's trying to find something, identified some boundary, but it's not good enough, which means that the algorithm is not capable to solve this problem. And maybe I forgot to mention this, but I have to emphasize it multiple times. Machine learning in many ways is an art form which allows us to play with the tools that we have until we solve the problem. And here what the algorithm is, this visualization showing is what kind of data is coming in. So at the moment the algorithm gets the information about X and Y. In this case, this means the coordinates along the x-axis and the y-axis. They call it x1 and x2. You can call it x and y if you want. It doesn't matter. And this information is fed into 2 neurons. These neurons analyze the data and pass the information to the next neuron, and the final neuron is giving the output. These are the neurons which initially have random values, and they don't do anything at the moment. So now if you add more neurons, which means let's try to add more complexity in the model, we can try to see what it can do. So magically, just adding 2 more neurons, so this is like adding 2 more brain cells, we're able to solve the problem. However, with only 2 neurons, we cannot solve the problem. And I can again demonstrate back. I mean, we have only 2 neurons which are trained to analyze the input. They don't do much. Every time they're getting some different result, but it'd be not perfect circle. We can add 1 more neuron. We see how it can perform with 3. And again, is able to find solution. With 3 was stable solution as well. Now, if you add more and more and more neurons, will just make the things more complicated. And this is what frequently is called overfitting. We don't want to create a problem which is way too complex. So adding extra layers, adding more neurons, all this will be able to solve the problem. However, it becomes more and more computationally expensive. And for this very simple problem, you don't need that much complexity. You just need only 2 neurons and 2 layers. And just also explain a little bit more what we're doing. Apologize, just a second. This is showing how the data goes. The data from left goes to these 2 neurons. They process it. They perform some kind of analysis, and after it feed it back to the right. So, and this, the thickness of the lines demonstrate which are important. So these thick lines show that here, in this case, most of the information is coming from X1, little bit information is coming from X2, and both of neurons are feeding a lot of information into the last neuron. Now, when you have 3 neurons, which actually can solve the problem, you can see that information from both inputs X and Y are fed up in the neurons. This neuron is getting information mostly from X2. This is normally getting information from X1. This is also getting information from X1. After that, they analyzed and provided to the end. So this is a very visual way to understand how neurons work. You're propagating information, and also you can see how the neurons look like. They generate some shapes separating boundaries between orange and blue, but they are not perfect. And even though you have 3 imperfect boundaries identified with these neurons, you have this boundary, and this boundary. At the end, when these 3 boundaries are combined, you're getting this not perfect figure, but you can see the shape of the boundaries that are identified by the neurons, how they combine to generate the last one. Now, if you try to solve more complicated problem, classification problem, now we have 4 regions. We can try to run it with this case. Now we want to identify region here and region here. Now we're able to identify this only boundary. We don't have enough complexity to identify both boundaries. We need to add more features, more neurons. Adding more neurons in one layer is not good enough. It's not helping. Let's try with 2 layers and and add more neurons in both layers and try to run it. And voila, with more complexity, with more brain power, we're able to identify the feature. And now you can see that here we have one of the neurons which actually is doing perfect job, was able to identify regions, and after that they further refined with the other ones. Does it make sense? Is it helpful, this explanation? Do you have questions at this stage? Because I think this is kind of very important stage of our presentation, and hopefully it's exciting for you or informative for you. No questions? Okay, I'll show also in other examples. Now, if you have only two regions like this, again, as you can guess, this would be very potentially solved to find the boundary between those two regions. But if you have very complicated region, which like these two spirals, which are intertwined, it'd be much more difficult to algorithm to identify the boundaries between those two features. And it's trying, it cannot find it, it's still, as you can see, it's pushing to the limits, trying very hard. The dog is chasing its leash, but is not doing very good job.
Hey, Monty,
Yes.
there were a couple questions in the chat. I thought they were good questions. The gentleman's asking where we get the data and what problems we're solving. So maybe going back to a higher level about what we're doing. Do you want to talk about that?
Yes. The key thing is what kind of problem we are solving. For this type of problem that I'm demonstrating at the moment, this is pre-wired to solve these four problems. I don't think there is a way to add additional data here. However, if you
Maybe more the problems that we're actually solving with our grants and the work we're doing for geothermal and stuff like that.
yeah, I mean, I'll show it in a little bit. But I'm just showing at the moment, Vertex AI is the platform that Google allows you to perform this kind of analysis. However, there is a lot of tutorials, there is a lot of explanations how to use it. I say, I mean, as you can see now, related to data sets, they already have data sets which are preloaded, but in many cases you need to upload your data set, the type of data that you need to provide, in what kind of format, there's some specific requirements. So at the moment, there is no like standardized way to deal with data, especially with complex scientific data similar to one which we're analyzing. If we want to analyze information about cats and dogs or handwritten different numbers, there are plenty of examples out there. So really, it's very much dependent on what you want to solve. And there are tools out there which allows you to upload your data and to perform the analysis. Here, the problem that we're solving, this is the second question. Here, we're really trying to solve classification problems, which means we want to find the boundary between blue and orange. You can think it is, again, the algorithm trying to find the pathway in a city or something else. And what I wanted to demonstrate that some of these problems really more complex, and there is no magic button or magic solution that you know in advance what kind of neural network will be sufficient to solve a particular problem. And you need to add potentially more data to be able to solve the problems. It's a challenge that you need to address in this process. And I'll say that there is no magical solution. And as I showed here, I mean, now adding more features, now you see the solution is getting better and better in identifying these orange and blue regions. Now understand that there is some spiral feature, but it's still not good enough. So maybe you need to add more layers and continue with this process until we're able to find a good solution. I hope it makes sense. So now, I'll show you a little bit more about the platforms that we are building, and I hope you see my screen. Is it? I mean, I'll try to increase the size. Do you see it well? I mean, I have no idea how well you can see. Is it okay?
Yes, it's good.
Okay. Just maybe to go back to, I mean, I'll just go to this slide to give you high level summary before I go there. So our company currently develops 6 different software or artificial intelligence machine learning frameworks. The first one is to characterize contaminants and how to remediate them. This is important for groundwater contamination, for air contamination, many cases that you have data which characterizes contamination existing in the environment. We have applied and developed machine learning methods that can help to solve this problem. The second project that we're currently actively working on is geothermal utilization. Geothermal is very important for the energy security of our nation and our move towards renewable energy resources. And we're developing tools which help people more efficiently to utilize their geothermal resources. This third tool is GeoML, and I'll be demonstrating both Geo2Go and GeoML. GeoML is for characterization of applying geochemical and geophysical data to characterize reservoir basins. And these are subsurface formation that are frequently used for different purposes, not only for geothermal, but they also can be used for carbon sequestration, oil and gas extraction, energy storage, waste disposal, water supply, multiple uses. And the challenge is because there are multiple uses and sometimes these uses can be conflicting, it's very important to have tools that can better understand the data which is available for the subsurface and what will be the most optimal way to be applied. We also working with NASA to perform artificial intelligence machine learning related to earth science models. Earth science models are very important not only for climate modeling, but also for predicting the amount of infiltration and precipitation and recharge and surface runoff occurring on a watershed scale. Upper Colorado watershed is one of the very important sources for water in our nation. feeding water for the Southwest, Arizona, New Mexico, California, Utah, Nevada. And we're analyzing data related to Upper Colorado watershed and trying to address how future climate changes can impact the water supply. We are currently starting 2 new projects, which are on the bottom, and one is to predict earthquakes, if you want to call it. This is kind of the ultimate goal, but at the moment we are trying to predict dynamics occurring along the fractures and faults using artificial intelligence and machine learning. And this is very, very challenging problem. We have the expertise to address these challenges, and we're just starting this project in February. And the last project that we're currently working is related to energy solutions in urban settings, application of geothermal, solar, and various alternative renewable energy resources in urban settings. So these are our 6 major goals, major projects and software development goals. And as I was showing, one of the tools that we're currently developing is GeoML. We want to be able to provide different data. So the top at the moment, this app, and everybody can use it. Actually, it's live on the web. I'm not going to put the link now because last time when we were making demonstration about this app, this is running on our compute servers, but sometimes they can be overloaded. As you can see, the bandwidth at the moment is kind of strange. So if a bunch of people start loading this app at the moment, this might break my presentation. So I'll share the link, but don't link at the moment to this. So in the future, people will be able to upload their data sets here. At the moment, we don't allow this because, again, we don't want to crash our system. Currently, we have information about 5 basins or geologic reservoirs in Michigan. And you can visualize this information. You can plot the data. These are the locations. We have information about reservoir thickness, so you can visualize information here. But more importantly, I mean, I'll just show another. So I'll go back to this one. So this is one of the reservoirs. And again, I can click and show what is the thickness of this reservoir. But what is interesting is that we can predict what uses will be the best for this reservoir. And to perform this, we use machine learning model. And this machine learning model is visualized in this interface. We can generate permeability field, and we can generate different random permeability fields. And once you generate a field, we can ask the algorithm to make a prediction if you have, in this case, 1 injection well, what is the maximum rate that you can inject so that the pressure within some radius, which is in this case 3 kilometers around the well, is below 1 meter, that the pressure doesn't change more than 1 meter. And you can, again, generate new field, make prediction, and you get different value. And all this is done in real time using machine learning algorithm. Machine learning algorithm assimilates the heterogeneity field and makes prediction what is the shape of the pressure propagation around this well and what is the optimal injection rate. And if you use only 1 well, it's one situation. If you use 2 wells, you can also make predictions when you have 2 wells. Now 2 wells can inject more because you can spread out and use the pool. Also, in some cases, it's convenient to have injection extraction pairs, especially for geothermal. When you want to extract heat, you have injection well and extraction well. And again, the system automatically predicts what is the optimal rate without creating unnecessary changes in the pressures. I see a question that most of data is open, but not all of it. I will reply right away. Currently, our tool is designed to work only with open source data. This is what we are demonstrating, but at the moment we are developing capabilities that we can do with proprietary data. So people will be able to log in to our interface with their Google or Facebook account. And when they log in, they'll have specific privileges and specific access to specific data sets. And if you have your own data or data that you have access to it with your privileges on the cloud, you'll be able to use this data. So we are working very actively on this. We have other small businesses to develop this capability. So it's a collaborative work, but we are working in this area. So what I'm just saying that this machine learning algorithm again can generate a random permeability field and make predictions. What is the best way to inject or inject fluids, which could be carbon sequestration, or extract heat with geothermal pairs. And after that, I mean, this is just like a demonstration tool here, but after that, you can predict for this particular reservoir what will be the optimal utilization. So now the algorithm, when we press solve, computes for this aquifer and every single location how much we can inject if you're using one well, or if we switch to two wells, will give us how much we can inject if you're using two wells. Or if you have geothermal heat production system of one injection extraction well, it can show you what is the optimal rate that in this system can operate. So this is high-level demonstration how using machine learning very quickly can analyze this data. And this is very fast process. So that's why at the moment when I do this right away gives an answer. Does it make sense?
So what's cool about what Monty was showing you is typically this kind of level of analysis is done by research institutions. And with our work, we're making an effort to bring it to the people, so to speak, so that anybody can have this data and figure out solutions without a very exclusive and high level of education and resources.
Yeah. I'm seeing another chat and I'm just reading it. Yes, Daniel Martinez, thank you very much for your question. Yes, the short answer is yes. So we're doing all these things behind the scenes at the moment. We don't, I mean, down the road, we may be allowing people to have more access to the machinery and to control how the machine learning analysis is executed. At least at the moment, we are kind of hiding most of the details. And mostly we haven't figured it out what would be the easiest way to allow users to have more control on the machine learning methods that are developed. And as I mentioned, they're kind of art. And also the training process is typically the most computation intensive. So if you want to build a new model, what you need to do is to use your privileges start the training process, which maybe take a day or a couple of hours, or if the data is large, can require even a month. And after that, when the training is done, you get notification that the new machine learning model is available for you to test it and see how it behaves. So the key for machine learning is that training typically takes a lot of time. The design and deciding how to really build the machine learning model is challenging. However, once you made it and once you're convinced that this is a robust machine learning model and has good performance, the execution of this machine learning model by itself is very fast. So the other question was, let us know when we can input government contract award data for analysis. Yeah, I mean, there are two ways to answer this question. One is when the tool is fully available, but the other answer will be to potentially collaborate if we really think that there is a good way to do this. We are kind of overwhelmed with the amount of work that we have to do, but we are always very open for collaborations. So if you think there is a way to collaborate and perform some of this analysis before the tool is fully functional, we can do this because we can perform all this analysis behind the scenes using our machinery. The GUI interface, the graphic user interface that I'm demonstrating really is because it's cool, but it can never capture all the complexity and challenges that we can address behind the scenes with our machinery. So I just want to show how we can also apply this for geothermal. So this is a different data set. This data set covers most of the Southwest. And this is Great Basin. Great Basin is one of the most highly potential basins for geothermal exploration. It's analyzed by many institutions. Numerous companies are exploring geothermal resources in this region at the moment. And there is also a lot of public data. The data sets that we are now analyzing, this is something like, I believe, 14,000. Yeah, 14,258 data points, which are distributed within data basin. You can see the location, light long, temperature, and a bunch of attributes that are measured in these locations. And we're analyzing this data to identify the geothermal prospectivity. So in this case, we're showing regions that we think that there is a high potential to have high temperature resources. These are the locations with red. So 0 to red is the scale is 1 is very high prospectivity and 0.1 and 0 very low prospectivities. So you can identify locations that we think that they are important for geothermal exploration. For high temperature, we can also identify locations which are good for mid temperature and low temperature. For geothermal exploration, in some cases, we need high temperature if you want to produce electricity. If you want to use the water geothermal, for example, for greenhouses or for district heating or municipal heating, then you don't need such a high resources. So depending on what your temperature needs, different regions are prospective for geothermal use. And this is what the algorithm is trying to identify. And people have been doing this forever. Subject matter experts may take years to perform this analysis. With our tool, we can do this much faster.
Well, and can I just add something there, Monty? What's really interesting about this is it can be showing you some resources that aren't that aren't on the surface. So you imagine a hot spring somewhere, you'll say, oh yeah, there's really good geothermal resources here, but something could be really hot subsurface and not be exhibiting that as a hot spring. And this tool would help you find those geothermal resources that aren't showing on the earth, but are there. So that's part of the magic of this. Sort of like finding a needle in a haystack.
And our goal down the road is to be able to, as I currently zoom in, and even have more refined solution, so you can almost go on a scale of a house or district within a city and see what is the geothermal potential in this location. So we really want to be able to facilitate the entire process to have more resolution. Also, the other thing that we are trying to do is to, for example, overlay information about power lines, because if you have electricity production, it's not only important to have good location, but it's very important to have close by power lines which allow it to transmit the energy to other locations. So this is, in general, how we envision and to further develop these tools and how to apply artificial intelligence and machine learning to solve these challenging problems. I think my mouth is tired of talking. I'm joking. I mean, I talk now for about an hour, and I think if we have more input or questions or discussion, this stage would be great. I mean, this is kind of the most important thing that we wanted to show today.
Yeah, we can tie it up. Thanks everybody for listening. Or are there any more questions? Okay, Sophia, are you there?
Yeah, I'm here. Well, if anybody is- doesn't have a question, so we can just close it up right here. Thank you so much for the presentation. There's a lot to cover. So I'm really grateful for all this data. And yeah, I mean, if someone else have question further, please send us my way. I can send it to Trace. Trace, just quick question.
Yes,
Can we share the presentation with the attendees, or you can?
I think so. Are you okay with that, Monty? Yeah, he said
Can
yes.
you can edit some parts that they're not, you know.
Yeah, I think it was fine. There was
Share, and then we can share it with the attendees.
yeah.
Yeah.
And
So-
yeah, feel free to reach out to us directly if you are interested in any kind of collaboration. You can go to our website and find our contact information there. nvtrace.com.
Great. Thank you so much, Trace, Monty.
Thank you. Take care, everybody.
Thank you, everyone.